In this video, we work a second example of optimization. We're still trying to find relative extrema, and this time we've got a polynomial function in x and y, and we're going to use the second partials test. So I just wanted to do one video where you saw an example from beginning to end, and this is it. So okay, I'm trying to find extrema of this function. The first thing that I need to do is find the critical points of the function. And remember, in Calculus 3, when you're finding critical points, that means you have to compute the gradient, of your function and then set the gradient equal to the 0 vector and solve the system of equations that results for x and y. You're looking for x-y pairs that satisfy this system of equations. It's represented by that single equation there. Okay, so that's the plan, and remember, it's because the slope in the x direction and the slope in the y direction have to be 0 at the same time for us to have a horizontal tangent plane. And when we have a horizontal tangent plane, that's a potential location of a minimum or a maximum, relative minimum or relative maximum. So first thing we do is we compute the gradient. And remember what the gradient is. It's just the vector of first partials. And so we need the first partial of f with respect to x and the first partial of f with respect to y. So we're treating y as a constant, and we are differentiating with respect to x this time. The derivative of x cubed with respect to x is 3x squared. The derivative of a constant times x with respect to x is just the constant. And this doesn't look like it, but remember, y is being treated as a constant. So this is a constant times x as well. The derivative of a constant times x is the constant, which happens to be 3y squared. And that's the partial of f with respect to x. And the partial of f with respect to y is this, just by definition. This time we're treating x as the constant and differentiating with respect to y. That's just constant. There are no y's in it, so the derivative of a constant is 0. That's just a constant with respect to y, so the derivative of that constant is 0. And then over here we've got a constant times a function of y. So remember from Calculus 1, if you have a constant times a function, you bring the constant down and you multiply by the derivative of the function. Derivative of y squared with respect to y is 2y. And so we get this. We get 6xy as the partial of f with respect to y. So we're setting the gradient vector equal to 0. And that is this vector. We've got 3x squared minus 3 plus 3y squared. And 6xy equals the 0 vector. And remember what that means. Both of these equations, or both of these partial derivatives, have to be 0 at the same time. So this is equivalent to saying, I need the slope in the x direction to be 0, and I need the slope in the y direction to be 0 at the same time. Now I think it's easiest to see when the partial of f with respect to y is going to be 0. Either x is 0 or y is 0. So I'm going to use that to come up with my cases and then substitute the corresponding values over here and then just see what happens to the other variable. Okay, so I'm trying to solve the system of equations now. So here's our first case, case 1. The partial of f with respect to y will be 0 when, well, we know when 6xy is 0, which implies that x equals 0 or y equals 0. So in our first case, we're going to choose the case when x equals 0. I guess case 1 is down here, really. Saying let x equal 0. Then if x is 0, the partial of f with respect to y is 0. And now we want to see what happens to the partial of f with respect to x. So the partial of f with respect to x is 3x squared minus 3 plus 3y squared. Well, if x is 0, we just get negative 3 plus 3y squared. And we need this to be 0 as well, because we need the partial of f with respect to y to be 0 and the partial of f with respect to x to be 0. So we set this equal to 0 and solve for y. Well, then we've got negative 3 plus 3y squared is 0. So 3y squared has to be 3. Just divide both sides by 3, and you get y squared equals 1. So y equals plus or minus the square root of 1, which is plus or minus 1. So you've got two critical points from this. When x is 0, we get y must be plus or minus 1. So xy equals 0, 1 is a critical point, and xy equals 0, negative 1 is a critical point from that first case. Okay, so we said earlier the partial of f with respect to y is 0 when this is 0, which means either x equals 0 or y equals 0. One of those is true. First case was x equals 0. Now let's see what happens when y equals 0. I call that case 2. So we're going to let y equal 0. Then we're guaranteed the partial of f with respect to y is 0. And then we'll look at the partial of f with respect to x. Now since y is 0, we get 3x squared minus 3 plus 3 times 0. And then we set this equal to 0 and solve for x. Well, I think we get pretty much the same system, or same equation as before. We get 3x squared equals 3. If we move that 3 to the other side, we're adding 3 to both sides. Divide both sides by 3. And then take the square root of both sides, and you get x equals plus or minus 1. So when x equals, or when y equals 0, x equals plus or minus 1. So we've got two more critical points. Now it is a coincidence that we have 0 and plus or minus 1 here, and 0 and plus or minus 1, or on this one as well, and we had that on the last example. They're not always 0 and plus or minus 1. I think those are just problems that are easier for textbook authors to invent. It's really hard to come up with problems like this that work out nicely, and they did, but that means you're going to see some patterns like that. Critical points are when x equals 1, y equals 0, and x equals negative 1, y equals 0. So all of our critical points, here's our list, are 0, 1, 0, negative 1, and 1, 0, negative 1, 0. So we need to test all of those. That's where we have a horizontal tangent plane. We have to test them and see, does this correspond to a min or a maximum in the original function? What about this one? What about this one? And what about this one? We'll test them using the second partials test. So we're going to go use the second partials test now. Now I have introduced you to the Hessian matrix. So we're going to compute the Hessian matrix. This is our higher dimensional analog, multidimensional analog of the second derivative. It's a matrix of second partials. And I'll just write that over here. For a function of two variables, it looks like this. In the first row, you take that partial with respect to x, and you differentiate it with respect to x and then y. And then you take the partial with respect to y, and you differentiate it with respect to x and then y. And you get this matrix. It behaves like a second derivative. And we'll see, I'm going to show you something kind of cool involving this in a little bit. Okay, so now I want to compute this, and then I want to evaluate my function I want to evaluate my Hessian at the critical points, and then we'll take the determinant, and we'll see what the determinant is, and that will allow us to determine whether each of those points corresponds to min or max. But what we need are the second partials. So first we'll write down the first partials. Partial with respect to y was 6xy. It was so short that it was easy for me to remember. Partial with respect to x is right here, 3x squared minus 3 plus 3y squared. Okay, so now I'm taking second partials. So you take the partial with respect to x, and you take its partial derivative with respect to x. Derivative of 3x squared with respect to x is 6x. That's a constant, so the derivative is 0. That's constant with respect to x whenever we're taking a partial derivative, so its derivative is 0 as well. So we get a 6x there. Partial with respect to x and then y means you take the derivative with respect to y, partial derivative with respect to y, of the partial of f with respect to x. Okay, there's no y in that, so we get 0. There's no y in that, so we get 0. Here, derivative with respect to y is 6y. Now, according to the theory, we know that the mixed partial, the partial with respect to y and then x, should be 6y. But this one's so easy, we might as well take this opportunity to check. This says take the partial with respect to x of the partial of f with respect to y, which is just 6xy. If we've done everything correctly, this should be the same as this. Well, that is a constant times x, the derivative of a constant times x is the constant, and the constant in this case is 6y. So those are the same, which is a very good thing. Okay, and now we'll look at the second partial of f with respect to y. So we're taking the partial with respect to y of the partial with respect to y. And this is a constant times y. The derivative of a constant times y is just the constant. So our Hessian matrix in general has these as entries. And now we will evaluate that at the 4 critical points. And then for each critical point, we will also compute the determinant of the Hessian. So we could write that this way, or we could write it this way. It looks like an absolute value, but it's not. Since this is a matrix, that's a determinant. It's a 2 by 2 determinant. So you multiply across one diagonal this way, you multiply across that diagonal, and you subtract. And then once you've computed D, then we go through the second partials test and we're able to state the conclusion. So we'll state the appropriate conclusion for each critical point. Okay, so that's the plan. Let's do it. And it's not too difficult at all because our critical points were 0, 1, 1, 0. They were pretty easy to remember. Okay, so let's try this one first. When x equals 0 and y equals 1, we get 0 here, 0 here, 6 here, and 6 here. Okay. Well, then the determinant of that is 0 minus 36. So you get negative 36. Whenever D is negative, that means you're at a saddle point. So f of 0, 1 is a saddle point. Now, to find the value of f of 0, 1, we need to substitute 0, 1 back into the original function. So I'm saying evaluate f at the critical point to find the minimum value, the relative maximum values, and to find the saddle point. Okay, f of 0, 1 is a saddle point, and let's look at our original function. It was right here, and we have x cubed minus 3x plus 3xy squared. So I'm just going to write that over here for us. Okay, so x is 0, so we have 0 plus 0 plus 0. Okay, so we get 0. All right, and now, so that was our first test. So that was the first critical point. I'm going to abbreviate that CP. We want to go through all four. F of 0, negative 1 is sure to be similar. If x is 0, we'll get, this is 6x and 6x on that diagonal. If x is 0, so we'll get 0 and 0 again. On this diagonal, we have 6y and 6y, so we'll have a negative 6 and a negative 6. Okay, well then the determinant of that, excuse me, is still 0 minus 36, which is negative 36. Of course, negative 36 is negative. So f of 0, negative 1, if x is 0, we get 0 for our function. That's 0. This is a saddle point. So that was our second critical point. Now let's look at our third. We look at x equals 1, y equals 0. So we had 6x and 6x. Well, I think I'll just write it down so you can see it. It's off the screen now. We're taking this matrix and we're evaluating it at x equals 0, y equals 1. Excuse me, x equals 1, y equals 0. So we'll have 6 there and 6 there, 0 there and 0 there. So the determinant of this guy is 36 minus 0, which is positive. And the second partial with respect to x at that point, that's 6, which is positive. So it's concave up in the x direction. And if it's concave up in the x direction and d is positive, then it's also concave up in the y direction. And this number here confirms that, concave up in the y direction. It's concave up in the x direction, concave up in the y direction. So that means we're going to be at a relative min. So f of 1, 0, and if I replace x or y with 0, that's gone. We'll just have 1 cubed, so the 1 minus 3, that's going to be negative 2, is a relative minimum of the function. Okay, that was our third critical point. And now we want to do the same thing for our final and last critical point. Final and last. Of course, it's final and last. Final critical point. And our final critical point was x equals negative 1, y equals 0. So we're evaluating this matrix again at the critical point negative 1, 0. X is negative 1, so we get negative 6 on that diagonal. Y is 0, so we get 0 and 0 on that diagonal. And remember, our function was x cubed minus 3x plus 3xy squared. Okay, now we'll take the determinant of the Hessian. So we get 36 minus 0. 36, which is positive, and the second partial of f with respect to x at that point is negative. So we said earlier if the determinant was positive, then these two partials would have the same sign. So it's concave down in the x direction because that's negative. And because the determinant's positive, it should also be concave down in the y direction. It turns out it is. You put those together and you know you have a relative max at that point. So f of -1, 0, that's -1 cubed minus 3 times -1 plus 3 times -1 times 0 squared. So that ends up being 1 plus 3, that's 4. That's a relative max. Okay, it's not too bad, guys. This is a very typical optimization problem. It did take us 20 minutes to work it without talking about any of the theory or background, but let's just go through an outline of the method really quickly. So first you need to find the critical points, which involves computing the gradient of f and then setting it equal to 0 and solving for xy. Now if you remember why that's true, we're basically saying we need the slope in the x direction to be 0 and the slope in the y direction to be 0 at the same time. That'll give us that horizontal tangent plane, which means we might have a relative min or relative max there, or we might have just a little flat spot like a saddle point. So we solve this system of equations, which usually involves factoring and looking at different cases. Say you've got this product and you say, how on earth could I get 0? Well, if any of the factors are 0. So you solve the system of equations, you go through all the possible cases, and that's going to get you a number of points. This time in this example we had 4 critical points. Now once you have the critical points, you need to determine whether each of those corresponds to a min or a max. So this is what we do next. We compute the Hessian matrix. This is our multidimensional analog of the second derivative. It's just the matrix of second partials. So you're just computing some second partials over here. You can do both of these mixed partials, or you can just say the mixed partials have to be equal. So that's a possibility. And then at each critical point, you substitute the critical point into the Hessian. You compute the determinant of that matrix. If that determinant is negative, that point is a saddle point. If the determinant is positive, well then you could have a relative min or a relative max. The determinant is positive, that means the concavity in the x and the y direction have the same sign. So if the determinant's positive, like in this example, and we see on this diagonal that it's concave up in the x direction and concave up in the y direction, well, that means we're at a relative min. And then on this example, we saw, well, the determinant was positive. Well, and that means, again, that the concavity in the x and y direction, they're the same. They have the same sign. They're either both concave up or both concave down. You just need to figure out which one it is. Well, it's concave down in the x direction. It turns out to also be concave down in the y direction. So the graph looks like this locally, and that point corresponds to a relative max. So that's how you do it. Please email me if you have any questions, guys, as you do this in your homework.